This is my presentation for the glider report for Zoe Robertson. In this presentation, I will discuss the research, planning, iterative design and testing process, and results involved in the creation of my model glider. The requirements are that it must fly at least 20 feet in front of me. No pieces should fall off at any point. It must be less than 16 by 16 inches. It can have no automation or propulsion system besides my hand, and it must be primarily made from the balsa wood we've been provided. And so here are some alternatives I considered for my design. For the wing shapes, I considered elliptical, delta, rectangular, and tapered wings. Elliptical wings are really good at minimizing drag, and they also allow the thinnest possible wing, but they're very hard to manufacture. And there's also delta wings, which are very strong structurally, but the low aspect ratio causes a lot of drag, and based on the shape of the materials we were provided, this would be difficult to manufacture. There are also rectangular wings, which are very easy to manufacture, especially because the wood we were given is already one big rectangle, but there is drag at the tip caused by the sharp corners of the shape. And there are finally tapered wings, which is the wing shape I used in my final design, which is a compromise between the efficiency of an elliptical wing and the manufacturability of a rectangular wing, which made it a very good choice for me. And so there's also the wing dihedral option, which is where the wings are abled up above the horizon instead of straight out, which helps to stabilize the glider because it will level itself out if there's a disturbance. But I chose not to use a dihedral wing because it would be more difficult to attach than a flat wing to the fuselage, and my glider was able to reach the minimum distance without it, so it wasn't worth the trouble. And so the adhesives I considered, in my final glider, I used adhesives to attach the wing piece, the tail, the vertical stabilizer, and the additional mass, and all of these components had different needs and limitations. I considered duct tape, Gorilla Glue, hot glue, and Elmer's glue. Gorilla Glue is very strong, and it takes up very little space, which makes it ideal for attaching the wings and the tail to the fuselage. I also used Gorilla Glue originally to attach my vertical stabilizer, but it broke off, so I used duct tape to reattach, which is also strong. And I used Gorilla Glue to attach the mass to the fuselage because it was very easy. And so the other adhesives I considered were Elmer's glue and hot glue because they're very easy to get, but they're much weaker adhesives and they take longer to set. And here's an overview of my design process. So for sizing, for my wings and tail, I chose to make them the maximum possible length, 16 inches and 8 inches respectively, both with a maximum root chord of 3 inches. And I did this in order to maximize the surface area of the wings, which would maximize lift within my constraints. And I left my fuselage at 15 inches long, which is the length when I got it, because I knew that that would allow me enough room to attach the wings and the tail. And I also used a 3-inch by 1.5-inch piece of balsa wood to make the vertical stabilizer. I just wanted it to be as long as the tail was wide, so I had as much space as possible to adhere it. And for balancing, I want the center of mass to be over the wing so it doesn't pitch forward or backwards. And to find the center of mass, I just balanced my glider on my finger until it was parallel to the ground. And I found that without any mass added, the center of gravity was over an inch behind the wing, which is problematic. And to fix this, I added small pieces of Play-Doh to the nose until the center of mass moved to be over the wing. And the center of gravity of my final iteration was slightly in front of the quarter chord of the wing. And my initial design included tapered wings and tail with maximum surface area to minimize drag and maximize lift, and a single wing piece with no dihedral to minimize the risk of wings falling off, and no additional mass or vertical stabilizer yet, and a tapered nose to minimize drag. And here you can see my first iteration. The slit for the wings was uneven, so the tail sat at a different angle than the wings, which caused the glider to lean right for every flight. And the center of mass was towards the back of the fuselage, not over the wings, which caused the glider to pitch up mid-flight and land weird on its back. Here you can see my second iteration. I shifted the center of mass forward by adding Play-Doh to the nose. I balanced rolling towards the right with a dime-sized amount of Play-Doh on the left wing, and to help the tail sit a little more flat, I added a little bit of Play-Doh to the right side of the tail, and it did fly more stable, and it no longer had pitch or roll issues, but it still wasn't reaching the 20-foot mark. So for my third iteration, I added a vertical stabilizer. I moved the mast to be over the wings, and the center of gravity was where I wanted it to be, and I sanded down the slits that held the wings and the tail, and they were able to sit flatter, so the remaining flights were straighter. And this iteration has no roll or pitch issues, and it reliably lands past the 20-foot mark. And so for my test flight, my best flight was on test day, and I did not remember to record it, so I don't have a video to show here. So an overview of the features of my final design. The materials are balsa wood, duct tape, Gorilla Glue, and Play-Doh. Most of the features are the same except for the cylinder of Play-Doh I added over the wings, and then the vertical stabilizer attached with duct tape. And here is the glider within a 16 by 16 square, so you can see it fulfills that requirement with the 1-foot ruler here at the bottom. And here is how I calculated my lift coefficient. We were provided this formula. I found all of this information, the mass, I calculated the wing platform area, the wing span, the average velocity from a few test flights, and then the air density. I plugged all of that in, and you see what my lift coefficient is, 0.155. And here's how I calculated my drag coefficient. You can see my lift coefficient over here, the aspect ratio I calculated with this formula, and then we provided the Oswald efficiency factor. And here is the formula I used to find the induced drag coefficient. I plugged this information in, and we found this. And we can assume that the induced drag coefficient is equal to the CD naught, and the coefficient of drag equals CD naught plus CDI, so it is just double the induced drag coefficient, and you can see what my final number is. And then the glider landed at 20 feet exactly, fully intact. It fits within a 16 by 16 square. It was propelled only by my hand, and it was primarily made of balsa wood, so it fulfills the requirements. And in conclusion, to summarize my report, I successfully created a glider within the guidelines that fulfilled the requirements through the use of tapered wings, vertical and horizontal stabilizers, and added mass. In the future, I would like to experiment more with fuselage lengths and wing designs and different positioning for the added mass to see if it can go further. And here's my bibliography. Thank you.